So we're going to continue. So we're looking at redox equilibria and what it's all about. So just to give you a synopsis of what is happening here, what we're saying here is that redox equilibria takes place when we have a reaction happening in the forward direction and the backward direction at the same time, right? So redox reactions are reactions that involve the transfer of electrons between species. For example, if a strip of zinc is placed in a solution of its ions, the zinc metal loses electrons to form zinc 2 plus ions. The electrons will stay on the surface of the metal, which becomes negatively charged. The zinc ions in the solution may then accept the electrons from the surface of the metal and be discharged as zinc atoms. So what that is saying is that whenever we put a zinc metal in a solution that has zinc ions, right? The zinc metal is going to lose electrons, but these electrons that the zinc metal loses is going to be picked up by the zinc 2 plus ions that are present in the solution, right? Now, the electrons that are released from the zinc metal, they are literally going to want to stay around the zinc metal itself. So because these electrons are going to stay around the zinc metal is going to develop a negative potential. We're going to get to it, but just giving you a preview. So the first thing that you need to remember is that the zinc metal is going to lose electrons to form zinc ions and electrons, right? Then these electrons are going to stay around the metal, causing it to develop a negative potential. Now, the zinc ions that are in the solution are literally going to accept electrons that are present around the zinc to reform zinc atoms. So that's what the equation here is showing. So the zinc ions are gaining electrons to form the zinc metal. In the reaction, a dynamic equilibrium is established when the rate at which the ions are leaving the surface of the metal is exactly equal to the rate at which they are being discharged on it again. So what that is saying is that the same rate at which the zinc ions are accepting electrons to form zinc atoms is the same rate at which the zinc metal or the zinc atom is going to lose electrons to form ions. So the same way the ions are gaining electrons to form zinc atoms is the same way the zinc atoms can lose electrons to form the ions themselves. Right? So when that happens, we have the rate of the forward reaction being equal to the rate of the backward reaction. So same way the zinc metal is breaking down to give us the ions and the electrons is the same way the ions and the electrons are then recombining to give us back the zinc atom. At equilibrium, there's a constant negative charge on the zinc and a constant number of Zn2 plus ions present in the solution around it. This charge difference that develops between the negatively charged zinc strip and the solution is called a potential difference. So what that is saying is that a potential difference will develop because remember we said that the metal is losing the electrons, right? But as they lose electrons, these electrons are going to stay around the metal itself. When the electrons stay around the metal itself, it's going to cause the metal to develop a negative potential. But remember now, in the solution, we have what? Zinc 2 plus ions. So there's a potential difference because what? The zinc strip is going to be what? Negative due to the electrons surrounding it. But in the solution, we have cations, which are the zinc cations. So that is how we get a potential difference there. So a less reactive metal does not form ions easily. It can develop a positive potential if equilibrium is established in the direction where the metal ions in solution take electrons from the metal strip to form metal atoms. So for example, if a strip of copper is placed in a solution of copper 2 sulfate, the copper develops a positive potential. The copper 2 plus ions in the solution accepts electrons from the copper strip, since there's a greater tendency for the Cu2 plus to reform copper atoms. So whenever you're looking at a less reactive metal, it's not going to be a similar case as the zinc one. Remember, zinc is going to more easily lose electrons, right? But when you are considering a less reactive metal, the metal is going to try to lose electrons because it has to, but it is not going to basically have the electrons surrounding it as it did for the zinc. So because of this, that metal is going to develop what is called a positive potential. Because remember, as we said earlier, the electrons that were present around the zinc is what gives zinc strip the negative potential. But for a less reactive metal now, the electrons are not going to stay around the metal, right? They are going to be literally accepted by the Cu2 plus ions in solution. And when the Cu2 plus ions in the solution accept those electrons, they are going to reform solid copper. So the less reactive metal will literally prefer a reaction in which the ions are accepting electrons to reform the solid metal. But for the more reactive metal will want to form ions, right? But the less reactive metal will favor forming the atoms or the solid itself. So because the electrons are not going to be surrounding the copper, it develops a positive potential. So the potential difference between the potential difference between a metal and a solution of its ions depends on the nature of the metal and the concentration of the ions in the solution at equilibrium. Zinc has a more negative potential than copper, as we said. That's due to the electrons that surround zinc, since it tends to form ions more readily than copper. Using the equation below, we say that the equilibrium from the zinc lies further to the left than the equilibrium for copper. So this reaction here is where we have the zinc losing electrons to form zinc ions, right? If we look at it in this direction. So this reaction lies more to the left, which is on this side. So zinc has a greater tendency to lose electrons. But this one now, remember we said it's the less reactive one. So as it gives up the small amount of electrons that it has, those electrons are going to be reaccepted by the ion, the cation that's present there, and it's going to give us back the copper solid. So I would say that this reaction here with the copper would favor the right direction, because it's less reactive, so it doesn't want to really lose electrons as the zinc. All right, so when you're writing the electrons are written on the left-hand side of the equation for redox equilibria. So for redox equilibria, you put in the electrons on the left-hand side. So here we have a beautiful diagram where we have zinc metal in zinc sulfate of concentration 1 mole per dm cube, and we have copper in copper 2 sulfate solution of concentration 1 mole per dm cube, and we have a nice salt bridge right here. We have the wire, right? Cape might give you this on the exam, so it's very critical for you to know it. So what is a half cell? In simple terms, a half cell is generated when you have a metal placed in a solution of its ions. So whenever we have a metal, let's say we have aluminum metal, and I decide to put the aluminum metal in a solution that has Al3 plus ions, right? That will literally create a half cell. If I get another metal such as iron, and I put iron, the metal iron, in a solution that has Fe2 plus or Fe3 plus present in it, then I have generated a half cell. So if I go again and I say I'm going to take magnesium metal and I'm going to put magnesium metal in a solution that has Mg2 plus ions, I am literally creating a half cell there. So a half cell is very simple for you to remember. It's literally where you have the metal placed in a solution that contains its ions. All right, it consists of a zinc half cell and a copper half cell connected by an external wire and a voltmeter and a salt bridge. The cells are usually drawn with the more negative electrode on the left-hand side. So we know that the zinc is the more negative electrode here because it has the negative potential. It will choose to lose electrons, right? And those electrons will be around the side. So that is why we put this one on the left-hand side. And then the copper one now is placed on the, all right, let me just follow through the notes. So the left-hand side is where we have the one that will more easily lose electrons. So since the zinc has a more negative potential than the copper, the electrons flow through the external circuit from zinc to copper. The zinc electrode dissolves in solution and the copper is deposited on the copper electrode. So what they are saying is that when the zinc gives up those electrons, right, it's going to travel through the wire, as some of them are going to travel through the wire. Remember, we said some is going to remain around the metal, but some will actually travel through the wire and go over to the copper. Now, because the copper is less reactive, the copper 2 plus ions are going to accept electrons and reform solid copper. So this electrode will increase in size because the copper ions in the solution here are going to accept electrons to form back solid copper. But the zinc is going to get smaller because the zinc metal is breaking down to give us the ions and the electrons. So here we have those reactions to show us what is happening at the electrodes. And please note that this is the electrode reactions. It's not the equation for equilibrium. So that is why the electrons are not on this side or are on the left side, because this is just the general reaction of what is taking place at the electrodes. So oxidation takes place at the anode, and that is confirmed because the zinc electrode is more likely to lose electrons. And then reduction takes place at the cathode because the copper 2 plus ions will literally gain electrons to form back solid copper. So the copper electrode is the cathode and the zinc electrode is the anode. So the electrons flow through the external circuit from the more negative electrode to the less negative electrode, so from zinc to copper. The overall cell reaction is you have the zinc metal here, and the first product you must have is the zinc ion. And then for the copper, you're going to have the copper 2 plus ions here because these are the reactants, right? The copper 2 plus is the one that's going to accept electrons to reform solid copper. A salt bridge hold on. So a salt bridge completes the circuit without allowing the two solutions to mix. So this is what we call a salt bridge. It connects these two half cells without causing them to mix. Let's see what's the purpose of a salt bridge. So it allows the migration of ions in both directions to maintain electrical neutrality. So the salt bridge is used to maintain electrical neutrality. A salt bridge may consist of a piece of filter paper soaked in potassium nitrate solution, or it may consist of a glass-shaped U-tube, not YouTube now that you watch, or a glass-shaped U-tube filled with agar jelly, saturated with potassium chloride. Easiest one here to remember is the filter paper soaked in potassium nitrate. But if you're that complex and stuff, you can literally remember the glass shape U-tube filled with agar jelly saturated with potassium chloride. So when a half cell loses electrons, so when the half cell loses electrons from the zinc, right, positive charges build up in the half cell. So we're going to develop a slightly positive charge in that half cell that is losing electrons. The NO3 ions, which is from the salt bridge, so if we were using potassium nitrate, the anion, which is NO3, or if we're using the potassium chloride, the Cl- ions would migrate from the salt bridge into this half cell to maintain electrical neutrality. So in other words, the salt bridge is like, oh, you're losing negative electrons. You're going to be a bit more positive here. I have to step in. I have to save the day. I have to maintain electrical neutrality. So the salt bridge is going to release the ions that are negative in order to reduce the buildup of a positive charge in that half cell. When the other half cell now, which would be the copper half cell, when this half cell gains the electrons, it's going to become negatively charged because it's gaining negative electrons. So what the salt bridge does now is that the salt bridge is going to release the cations in this case. So the cation would be the potassium cation, and it's going to basically neutralize the buildup of the negative charge there. So let's sum it up. Whenever we have electrons being lost from one half cell, let's say the zinc half cell, the cell is going to become a little bit positive. So to maintain electrical neutrality, the half cell has to step in here. So the half cell can be potassium nitrate or it can be potassium chloride. If that half cell loses electrons, it's going to get the slightly positive charge. So the salt bridge is going to release the anions to that half cell to make it a little bit balanced. Because remember, it would have been a little positive. So the anions will neutralize that charge. Now, if another half cell is gaining electrons, it's going to become slightly negative. So what the salt bridge does is it releases the potassium ions over there in order to reduce the negative charge buildup. So the potassium nitrate, potassium chloride, and sodium chloride are suitable salts that can be used in the construction of a salt bridge. Since they are very soluble and does not react with other ions commonly used in the electrochemical cell. So because these are soluble salts and they do not react with other ions in the cell, they are suited as salt bridge or salt bridges. It is important to note that ions pass through the salt bridge while electrons move through the external wire. So remember, whenever say any electron move through the salt bridge now, because the salt bridge is made up of potassium nitrate or potassium chloride or sodium chloride. So it's ions alone that the salt bridge literally moves. It doesn't move electrons. Electrons flow through the wire. So the ions will be moving here and electrons will move here. Electrons move from anode to cathode. Okie dokie. So a flow of electrons in the external circuit indicates that there is a difference in potential between the two electrodes. This difference in potential is called an electromotive force. So the electromotive force is basically a difference in potential between two electrodes. So remember we said that the potential difference is between two half cells, right? But the electromotive force is between two electrodes. So one is between half cells, which is the potential difference, and then the other one, which is the potential between two electrodes, that is called the electromotive force or the EMF, and is measured in volts. A high resistance voltmeter is used to measure the EMF. It uses negligible current, therefore registering the maximum potential difference. The EMF of zinc copper cell is 1.10 volts, and under standard conditions, under standard conditions. The standard conditions are 25 degrees Celsius and 1 mole per dm cube. So remember now, the electromotive force, or the EMF, is just the potential difference between two electrodes. So the electrodes themselves, not the entire half cell. All right, so the half cells and the EMF for the electrochemical cell can be represented as shown below. So instead of drawing out that big cell that we saw up there, we can just have a shorthand notation for it. So the first thing that you're normally going to write is the anode. The anode is present on the left. And then this here is the wire, right? And then you're going to have the zinc ions in the solution. Then you're going to have the salt bridge here. And then you know that the copper ions have to come first because they are the ones that are going to be accepting the electrons from over here. And then these will accept electrons to form solid copper, right? So you write your anode first, the ion that the anode produces, then you put your salt bridge, and then you start with the ion produced from the cathode, and you put the cathode itself over here. So it's literally all right, how can I put this for you to remember now? So you have metal to form ion first, and then you have ion to form metal next or last. So metal to form ion, and then ion to form metal. Metal to form ion, ion to form metal. And you must put your salt bridge in between. All right, so we're going down to She now. So the She that we're talking about is the standard hydrogen electrode. The potential difference, or the EMF, of a cell is the difference in potential of two half cells. So remember, we said that the potential difference, I don't know why they came down here with EMF, but it should just be potential difference. So the potential difference between two half cells, right? Oh, sorry, the potential difference is the difference in potential of two half cells. So whether one is more negative or whether one is more positive, the electrode potential of a single half cell cannot be measured by itself. However, if we assign an electrode potential of a half cell with an arbitrary value of 0, the electrode potential of other half cells can be measured with reference to this standard. So it's impossible for you to literally create a half cell by putting a metal into a solution containing its ions, and then you expect to measure how much electron is moving, therefore how much charge is being produced. It's very impossible for you to do that using just a single half cell. So what happens is that we introduce a standard that is called She, the standard hydrogen electrode. This electrode has a potential value of 0. So you know that if we connect, say, the zinc half cell to it, it can tell us how much electric current is being produced from the zinc half cell, because remember, its value would have been 0. So any increase that we see would just be coming from the zinc half cell. All right, so the standard hydrogen half cell, also called the standard hydrogen electrode, is used as the reference half cell and is assigned a potential of 0 volts. It consists of hydrogen gas, right? Consists of hydrogen gas. Am I missing something from this one? Let me check. Alrighty. So I think I'm missing something from that part. Let's see if I cut it off. I did. Alrighty, 1 minute. Just a minute, ladies and gents. Oh, I wonder if I can find it, the diagram down here. Yeah, perfect. So I don't have to go through all of that hassle, right? So the standard hydrogen electrode She, it consists of hydrogen gas. And this is how we normally draw She. So She is usually represented this way. You have the hydrogen gas coming in. She is also made up of platinum wire, and then you have platinum covered in porous platinum to increase surface area. The concentration of this half cell, which is She, or the standard hydrogen electrode, it must be 1 mole per dm cube, and it must be at a temperature of 25 degrees Celsius, right? And the pressure of 1 atmosphere is because it's standard. When something is a standard, all the conditions are kept constant. All right, so this is She right here. So you put your hydrogen gas coming in. The 1 bar is basically telling you the amount of pressure that's coming in with the gas, or the amount of gas coming in. And then you have the platinum wire, and then you have platinum covered in porous platinum to increase surface area. You have a saw bridge that connects it to any other half cell that you want to find out the potential for. So in this case, it's the zinc half cell, and you know that a half cell is generated when you have the zinc metal placed in a solution with zinc ions, and then you have the wire connecting both half cells. So the electrons are moving in this direction because the electrons will move from the more negative electrode to the less negative one. And the reason why you're seeing this on the right side is just because they wanted to show you She in this case. But you normally put this one on the left-hand side and then this one over there. All right, but it doesn't matter once you can remember. All right. Oops. All right, so we're continuing. So I'm going to go down to this one. So whenever we connect a copper half cell to the standard hydrogen electrode, we get a voltage of 0.34 volts. Since copper is a positive terminal, the standard electrode potential for copper half cell is positive 0.3, and this is written this way. So whenever you're writing the reactions for the less reactive metals, remember it's the ions that are going to accept electrons to form the solid, right? So copper is not going to be as negative as zinc because copper doesn't really want to lose electrons, right? And we call this the E cell value. So whenever you see a capital E with a knot, it's E cell value. So the E cell value, or the potential value here, is plus 0.34. Let's go down to the zinc now. So when the standard zinc half cell is connected to the standard hydrogen electrode, the voltmeter registers an EMF of 0.76 volts. In this cell, the reactions at the electrodes are as follows. So you're always going to have this reaction happening in the standard hydrogen electrode, or She. This will always be happening in that half cell. So hydrogen ions are literally just going to pick up electrons to form hydrogen gas. That's all that's going to happen in She. And whenever you connect a half cell such as zinc, because the zinc is more negative, it's going to release electrons and form zinc ions. So you can just remember this for the standard hydrogen electrode, otherwise called She. Hydrogen ions are literally accepting electrons to form hydrogen gas, and that's always going to be the reaction. All right, so the electrons flow from the zinc half cell to the standard hydrogen electrode. Thus, the zinc electrode is negative. Since zinc is the negative terminal, the standard hydrogen potential for zinc half cell is minus 0.76 volts. So because this half cell is more negative, the E value or the E naught value that we get has to have a negative sign in front of it, right? Because remember, the one that is more reactive will have a negative potential value. So the E naught value for that will always be the most negative. So when the standard hydrogen electrode is connected to the zinc half cell, the electrons flow in the opposite direction to that which occurs when it's connected to the copper half cell. So what that is saying is that for the copper half cell, copper is not going to give you the electrons. So the copper is not going to give up electrons to the standard hydrogen electrode, otherwise called She, right? It's literally going to favor the cation, which is Cu2 plus ions, accepting electrons to form solid copper. So it will more likely to pick up electrons that are released. And remember, those electrons are released from the said copper metal itself. All right, so let's go down to measuring E naught or E cell of half cells involving no metal. So some redox systems do not involve metals, but involve ions of the same element in different oxidation states. For such systems, a platinum electrode is immersed in a solution containing 1 mole per dm cube of both metal ions. So if it is that we have a half cell that does not involve a metal, right? It's going to be a little bit different for us to measure the E naught or the E cell value. But let's look at this example. So let's say we have ions instead of solid metal produced in the solution, or solid metal in the half cell. Let's say the two half cells only have ions that can accept or lose electrons. If we have the Fe3 plus Fe2 plus half cell, you must use platinum as the electrode because those are not the solid metals now. So the electrode would have to be made up of platinum immersed in a solution containing 1 mole per dm cube Fe3 plus ions and 1 mole per dm cube Fe2 plus ions. So you're literally making up half cells with these ions, right? So the electrodes are literally just different in this case in that you're using platinum, but the platinum will still be in a solution of these ions. So one half cell will be platinum with 1 mole per dm cube solution of Fe3 plus, and then the other half cell will be Fe2 plus in a 1 mole per dm cube solution of Fe2 plus ions. The standard electrode potential of Fe3 plus Fe2 plus half cell can be measured by connecting it to a standard hydrogen electrode. In redox systems that involve nonmetals in contact with their aqueous ions, a platinum electrode is used. So if you're looking at the nonmetals as well, and you're making a half cell with it and you literally don't have a metal, the easiest resort is platinum. All right, so for example, the bubbling over a platinum electrode immersed into a solution of H plus ions under standard conditions. So hold on. Yeah, this is for the She. All right, so I need to get that example. 1 minute. Where is my document? And I'm using the textbook as well. That's the key for both units. It's in the group. It. Redox Equilibria. All right, so we're at Topashi, for example. Oh, it's actually right. So for example, the bubbling over a platinum electrode immersed into a solution of H plus ions under standard conditions. Standard conditions are gases must be 1 atmosphere. As I said earlier, concentration must be 1 mole per dm cube. Temperature must be 25 degrees Celsius. Platinum is used as the electrode if a metal is not included in the half cell. Equilibrium is established between hydrogen gas and the H plus ions in solution. So if it is that we have hydrogen gas and we want to make a half cell, remember we have to use platinum as the electrode. So what is going to happen in that half cell is that the hydrogen ions are going to accept electrons to form hydrogen gas, and the E cell value will be 0 because this reaction actually corresponds to the She value, right? Because remember, we said She has an E cell value of 0. So here they are showing you the standard hydrogen electrode. You have the platinum wire, hydrogen gas coming in. As the hydrogen gas passes over the platinum wire, it's going to be converted to H plus ions and electrons, right? But the reaction is going to lie to the left-hand side. So the hydrogen ions are going to, no, let me correct myself. So you're going to have the hydrogen ions in this solution as the electrons come in, because this hydrogen gas is going to pass over the platinum. So during that process, you're going to form electrons. The electrons are going to react with the H plus ions in this solution. So you have the platinum foil covered in porous platinum. Temperature is 25 degrees Celsius. Concentration 1 mole per dm cube, and they normally use dilute sulfuric acid. The platinum electrode is an inert electrode and does not form platinum ions. It consists of platinized platinum, which catalyzes the reaction. So down at the bottom here, that's what they're referring to. You literally put in platinum and platinum. So platinized platinum means that the platinum metal is coated with finely divided platinum to increase its surface area for equilibrium to be established in a short time. So that's why they use so much platinum. The standard electrode potentials of other half cells can be found by connecting them to the standard hydrogen electrode, measuring the potential difference of the cell. And we said that earlier. So we're moving down to the standard electrode potential, which is known as E cell or E naught of a standard half cell. So E naught is the potential of that half cell relative to a standard hydrogen electrode. So it's literally the potential value that you measure when you connect it to She. All right, so any value you get whenever you connect a half cell to She, that is what we call the E naught value. The standard electrode potential of copper ions in copper solid half cell is measured by connecting it to a standard hydrogen electrode. The standard electrode potential of copper ions in copper half cell is the potential difference between the standard hydrogen half cell and the standard copper 2 plus half cell. In this cell, the reactions at the electrodes are as follows. You have the hydrogen gas converting to H plus and it's also releasing electrons. And in the copper half cell, you have the copper ions accepting electrons because the copper does not like to lose electrons. All right, so the standard hydrogen electrode will literally act as the anode in the case of a less reactive metal. So this one, which is a standard hydrogen electrode, which is She, is going to give up electrons to the other half cell because it's less reactive. In other words, it doesn't really want to lose electrons. So the She now just step in and say, okay, let me help you out now and give you some electrons so that you can become stable. So the electrons flow from the standard hydrogen electrode, right? Hold on. So the electrons flow from the hydrogen electrode to the, hold on, give me a minute. I don't like how I copied that document at all. Alrighty. Where is it? Oh, I think I sent it to myself. I think I sent it to myself one time. I really have to resend it to myself. Right, so we're back on track. Sorry about that. Just want to ensure you follow. All right, so we were at this. So the electrons flow from the hydrogen electrode to the, hold on. God have mercy. I say through that already. All right, so the electrons will flow from the She over to the copper. That's what they're saying. I don't want to confuse it with this part because this part looks like it is from another example. Yeah, so this is 189 and this is 187. Yeah, so that's a little bit confusing there. All right, I need to show you how to calculate E naught values. All right, so that's the last thing that we're looking at. So how to find E naught value. That's what CAPE will literally give you. What we discussed above were just some examples. So the one with the bromine was just another example. All right, so we're not looking at that one. So we're looking at the uses of standard electrode potentials. So standard electrode potentials are used to measure the strength of oxidizing and reducing agents. So it can tell you how strong something is how strong something is as an oxidizing or a reducing agent. The standard electrode potentials of redox systems are arranged in order of its values to give the electrochemical series. They give a measure of the relative oxidizing and reducing strengths of species, and the standard electrode potentials of some redox systems are shown below. So we have these elements and you are seeing their electrode potential values, right? Remember that the more negative this substance is, the more likely it is to lose electrons. So if something is more likely to lose electrons, it would be acting as a stronger reducing agent, because reducing agent reduce something, but they in turn are oxidized. All right, a negative value indicates that the species lose electrons more readily than hydrogen. This means it is a better reducing agent, as we said earlier. A positive value means that the species gains electrons more readily than hydrogen. So you see all of these values up here that are positive, it represents these species being able to accept electrons rather than losing the electrons. All right. This means that it is a better oxidizing agent than hydrogen, because oxidizing agents are substances that will oxidize something else, but they in turn will be reduced. In other words, they in turn will gain electrons. So using the following standard electrode potential values, we have it for zinc, we have it for copper. We can say that zinc is a stronger reducing agent than copper because its value is more negative, and then copper now would be a more stronger oxidizing agent than the zinc because its value is more positive. So the positive one is a stronger oxidizing agent, the more negative one is a stronger reducing agent. All right, so the standard electrode potential values can be used to calculate standard cell potential. So when two half cells are connected under standard conditions, the maximum potential difference between the two half cells is called the standard cell potential. Very important for you to note that the standard electrode potentials of the half cells can be used to calculate the standard cell potential. Right? So you're using the standard electrode potential to calculate standard cell potential, right? So if we look at the example below, using the standard electrode potential of zinc and copper half cells, the standard cell potential of zinc copper cell can be calculated as follows. So you have the standard electrode potential for for copper half cell being plus 0.34, and then the standard electrode potential of zinc is minus 0.7 volts, 76 volts. The E naught value that carries a more negative value is the negative electrode. So we know that the zinc one here is the more negative electrode. While the copper one would be the positive electrode. Electrons will therefore flow from the zinc half cell to the copper half cell. The equation for the reaction at the zinc electrode is the reverse direction, thus the sign of the E value will change. So what they're talking about is, if it is that you got a table looking like this on your exam, right? And you have this reaction here. This reaction is showing me reduction, right? So if I want the correct reaction, I have to flip this equation around. So the zinc would basically be losing the electrons, right? So what they're saying here, wait, hold on, I'm going to. So the zinc electrode, where am I? So the equation for the reaction of the zinc electrode is the reverse direction, thus the sign of the E value changes. So whenever you see the booklet that you're going to get in KEEP, they're going to give you all the reactions in terms of reduction, because it is called the reduction table, and it's similar to something I gave you earlier in the course. They're going to give you the reduction reaction. So zinc ions will be on this side, and you have to flip it because zinc will more likely to lose electrons, right? So whenever you flip that equation, in order to find the E cell value, you have to flip the equation to make it positive, right? So we flip the equation that we saw above to make zinc the reactant. So the zinc is losing electrons. So that is why the value is no longer negative, it's positive. Because when we flip the equation, the number is going to be flipped. And you only do this for the one that is more negative, or the one that will lose electron. So to find the standard cell potential now, all you do is to add the electrode potential of the copper and the zinc together after you flip the one that will show oxidation. So I flipped the one for zinc, so it became positive, and I get a value of positive 1.0 volt for this entire electrochemical cell, right? So don't mind the order. We normally, remember I told you earlier, you can put the anode, and then you have the ion that the anode gives up, and then you have the ion at the cathode, and then you have the metal at the cathode. So don't get confused by that. So all you do is to add it, but you must ensure that you look on your booklet, right? And you see if they give you reduction reaction, you have to flip that, and then the sign changes. This means that the EMF of an electrochemical cell can be calculated from the standard electrode potential. The Daniell cell, which has a similar arrangement to the zinc copper half cell, to the zinc copper electrochemical cell, has a value of 1.10 volts. So last thing is that standard electrode potential values are used to predict possible reactions. So they can tell you which reaction can take place from which ones can't. A reaction will only be feasible. Feasible is that, is it likely to happen? Can it happen? If the EMF value that you find is positive. So if we had added both of these and we got a negative number, it would tell us that that reaction or that half cell cannot be basically used because it's not going to give any reaction. So the overall positive potential of the cell suggests that the reaction is energetically feasible. That's speaking of this value here. So because it's positive, this reaction is likely to happen. So this means that the zinc reduces the copper to copper atoms while the zinc is oxidized. A negative EMF implies that the reaction is not feasible. So whenever you see the E cell value being negative, it's not feasible. So let's look at this example. How iron 2 plus going to form iron. Of cobalt going to form cobalt, right? Looking at these two values, which one of them is the more negative one? Clearly, it is going to be this one up here because it's a larger negative value, right? So because this one is more negative, I know that this one has to show me oxidation, or I know that this metal is more reactive than this one, right? So I have to flip this equation to show that the iron is going to lose electrons. So when I flip this now, the sign is going to change to positive 0.44. And then when I add the 0.44 to the minus 0.28 from the cobalt reaction that remains the same, I get plus 0.16. So the reaction is feasible, right? Because it's feasible because the E cell value that we get is positive, right? It will not be feasible because the overall EMF is negative as calculated below. So if we have this reaction here, where they gave us the cobalt being plus 0.28, and let us say that the iron was minus 0.44. If we were supposed to just add the values like that, add them exactly how they gave us. Well, they gave us differently in this case. So remember, both of the values were negative first, and then we flip one for it to become positive. In this case, they gave us positive for the cobalt and negative for the iron. So when we add both of those values now, we're going to get a negative value because this reaction can never take place, right? You can never have the zinc, the cobalt losing electrons to give the iron. That's not possible because the iron has the more negative value. So it is the one that's going to give up the electron. So this doesn't make any sense. And the E cell value is negative, telling us again that it's not going to happen ever. So if we consider a copper zinc cell where we have copper 2 plus ions and they're gaining electrons, the E naught value is positive 0.34, and the E naught value for the zinc is positive 0.8. Which one of these is more negative? It would definitely be this one up here. Or I would say which one of them is less positive, right? So which one of these values is less positive? It would be the top one. So the top one is more likely to lose electrons to the bottom one. So I will have to flip that equation. When I flip it, the sign of the E naught value changes. And then when I add it back to the 0.8, I get positive 0.46 volts. So it indicates that that reaction is feasible, and the silver equation is multiplied by 2 to balance the overall reaction. However, the E naught value remains the same. So when you add a coefficient to balance your reaction, it doesn't change the E naught value. All right. So let's say they gave us the copper having positive 0.34 and this silver being minus 0.8. That would give us a negative value, meaning that the reaction is not feasible. So remember that now. Positive E naught value, when you add them, if it's positive, it means the reaction is feasible. If it's negative, it means the reaction is not feasible. So the effect of concentration of on electrode potential. The values of standard electrode potentials are measured under standard conditions. However, changes in concentration, temperature, and pressure will affect the values of electrode potentials. Standard temperature and pressure may be maintained, but all right, so the standard, however, changes in concentration, temperature, and pressure will affect the values of the electrode potentials. The standard temperature and pressure may be maintained, but as soon as a reaction starts, the concentration of the reactants and the products change. So if we look at this reaction down here, right, where we have the copper 2 plus ions gaining electrons to form copper solid, if the concentration of Cu2 plus ions decrease, according to Le Chatelier's principle, the equilibrium would shift to the left to give us back more of the Cu2 plus, right? Therefore, the E naught value of the half cell would become more negative. In other words, less positive. The electron potential of the copper immersed in 0.1 mole per dm cube copper solution will be reduced to 0.31 volts. So this only happens when we disturb the system or when we add a stressor to the system. All right, and that is where we will end. I hope this added a little clarity. All right, all the best.